Hi guys, welcome to Learning Electronics Repair. You've seen this PCB before if you watch the channel regularly. So this is from an amplifier which was taken from a three-way active speaker. So bass, mid and tweeter speakers in there. There's three amplifiers in this. And this is faulty. So we have a burnt resistor. I'm sure you can see that there. We have a bridge rectifier, another resistor, a capacitor, 400 volt, 470 nanofarad, and the bridge rectifier, plus the electrolytic capacitor. You can see clearly that the resistor is burnt. And also this capacitor is domed. Can you see the top of it? It's not flat. So the capacitor has failed as well. This I'm pretty sure is just glue. It's not gunk out of the capacitor. Bridge rectifier looks okay, as does the resistor, as does the capacitor. What this PCB actually does, it fits onto this panel which goes onto the back of the speaker. So you can see here we have a power con connector in and the pass-through out, or link as it calls it. So this is where the mains comes in. It says here this is 220 to 240 volt. Volume controls on here, the audio in and pass-through are also on here. And some LEDs, so power on, and then the limiters for each of the three amplifiers, okay? High, mid and low. And this PCB, you can see is connected to the power coming in. If you look, you'll see effectively power coming in passes straight to power going out. So that's just a pass through, and also to here. So this connector goes down to the main amplifier unit, the three amplifiers, switch mode power supply. So that's the mains going down into the amplifier. And then this little thing, which plugs onto one of the PCBs in the amplifier, is connected to the opto isolator. Yeah, you can see there it's connected to there. The other side of the opto isolator, the LED, goes into the bridge rectifier. I'm sure you can see it connects into there. And the high voltage capacitor connects from the AC mains into the bridge rectifier. So there was some discussion about what this does. Originally I thought this was to detect maybe 220 or 110 volt mains, but the unit says it's 220 volt only. So it's not doing that. I'll show you the schematic for this and then just explain what I think it does. But particularly, I want to explain how this works because there was some interest in this circuit, which is known as a capacitive dropper. Here we can see then, this is the power con, live neutral coming in, linked just back to live neutral going out, so you can connect it to another speaker. You can daisy chain these. These are the two connections which go down to the switch mode power supply unit and the amplifier part of the cabinet. We have the 470 nanofarad capacitor, 400 volt, into the bridge rectifier, and from the other side of the AC on the bridge rectifier, the 1K resistor back to neutral. So that is the current path into the bridge rectifier. Now you may say, well, the capacitor is an open circuit, how does power get into this? Because you don't normally have a capacitor there. Yeah, I mean, you don't have that. So what's going on? Well, this circuit, the capacitive dropper, will only work with an AC input. That's the first thing. It has to have an AC input. And what happens is, as the voltage here, sine wave AC, alternates, this capacitor will charge in one direction and then discharge and charge in the other direction, and then back in the first, and so on, at the frequency of the mains, in my case 50 Hertz. So this capacitor is continually charging and discharging, and then charging the opposite direction. Yeah, AC. So current is flowing backwards and forwards through here as this charges and charges the other way and discharges. And that limits the amount of current that can go into this circuit. And by limiting the amount of current into the bridge rectifier, it also limits the voltage coming out of it. So that's what this does, it drops the voltage. This is something like a 1 watt 1K resistor, so brown, black, red, 1 0 and 2 more zeros, 1000, so this is 1K, probably a 1 watt resistor. And what that is actually doing is limiting the inrush current when you first power up, because when you power up, this capacitor will be discharged, okay? And if you just happen to power up at the instance the voltage up at the peak, yeah, peak voltage for 220 volts being about 320 volts for 220 AC, you'll get a sudden surge of current through this capacitor while it charges, and that will flow through the bridge rectifier. So in here we have the diodes and the bridge rectifier, and you could damage the bridge due to that surge of current. So this is what this is actually doing. It's just limiting the initial surge of current. It's not really acting there to drop voltage. It will get warm because there's current flowing backwards and forwards through it, which is effectively limited by the capacitor. In other words, the higher the capacitance, the more current. So that's what that's doing. On the output then, we have rectified, pulsed DC, but this is not 320 volts DC. This is much lower because of the limiting factor of that capacitor. And in any case, this capacitor is a 16 volt 470 mic. So this voltage, which actually wouldn't look like that because it's smoothed by this capacitor giving a steady DC, is going to be no more than 16 volts. That's the maximum rating, okay? So you can see just by the design of this that that must be limiting the current and therefore limiting the voltage, yeah? So that's what the capacitive voltage dropper does. 2 points I'll mention. What this circuit doesn't do is isolate this side of the bridge from the mains. Yeah, I mean, you connect it here through the diodes and the bridge rectifier. So, although it says live and neutral, and bear in mind the plug can be reversed in the EU anyway, effectively the AC is on both of these. So, if you touch this with your fingers and you happen to be grounded at the same time, you're liable to get a nasty shock. So this sort of circuit, in this case, is designed to be on a unit which is inside the amplifier. You can't touch this, okay? And the connection which goes down to the actual amplifier board is from the other side of this opto isolator. So from here onwards, it is isolated. The opto, by the way, isn't just a photo transistor. It's a photo Darlington. This is a Darlington type transistor in here, okay? To give a high gain, just draw it like that, like 2 transistors in series, photo Darlington. So that's the first thing I'll mention. The other thing I'll mention, if this circuit was like this, okay, with one diode, you might think that this would actually then power your opto isolator. Okay, that's where the resistor goes. This resistor, by the way, limits the current through the LED, obviously, I would hope. Yeah, you might think that that would actually work as well, because what we're doing now is just half wave rectifying the AC that's coming through this capacitor, whereas we're full wave rectifying. And now you're thinking, well, it's only lighter than LED, basically. Why don't just do that? Because it's cheaper. That won't work. What will happen with this is that when the AC is passing on the positive half cycle, it passes through the diode and charges the capacitor. On the negative half cycle, this diode won't conduct. So there's no path back that way, so the capacitor can't discharge. So what this circuit would actually do is charge the capacitor up to the full mains voltage and blow up the capacitor and the LED, of course. So that doesn't work. There's got to be a current path so that the capacitor, in this case with the bridge rectifier, can charge and discharge both ways. Okay, so that's how the circuit actually works. What does it do? Well, it's not there as my initial thought to determine if it's on 110 volt or 220. All this seems to do is to send a signal. This goes in the signal into the amp to tell the amplifier the mains is applied. Well, it probably knows its mains apply for the simple reason because, well, if there wasn't, it wouldn't know anything because it's not powered up, yeah. I think more likely this is designed to detect brownouts or low voltage supply because obviously if the supply is too low, this capacitor can't pass enough current to charge that up enough to light the LED. And that will depend on that resistor. And that's the one that's burnt, okay? So choosing the right value of resistor here will effectively determine whether there's enough voltage in this capacitor to pass enough current through the LED to light it up. So my guess, guys, brownout detector. But you know, get down there and let me know what you think. Now, this resistor that's burnt up, let's look at that. We can see the burn through there. We can measure it. And we will see it's open circuit, okay? It is open circuit. And the resistor, I can see brown, black, green, yellow, okay? And I initially said, oh, it's a 1 meg resistor. 1, 0 and 5 more zeros, 1 meg. But that doesn't make sense that it's 1 meg. Because this circuit for the LED and the opto isolator has less than 16 volts. That's the absolute maximum. It may be 12 volts or something like that. You wouldn't really have a capacitor so close to its rated value in here. So that, you would think, an LED, 12 volts, 400 ohms, something like that maybe. It's not going to be a 1 meg resistor. It doesn't make sense. There's something else that doesn't make sense about this if it's a 1 meg. 1, 0 and 5 zeros. And then we have yellow. Yellow is 4. And that would be the tolerance if it's yellow. And yellow is not a valid tolerance for a resistor like this, really. Gold is 5%, but, you know, it probably isn't the tolerance. This probably reads the other way. 4, 5 and no zeros, yeah? 1%. But then even that doesn't totally make sense because a 1% resistor would probably be with 5 bands anyway. 45 ohms isn't a common resistor value. So I'm going to take this out and have a look on the other side of it to see if I can see any sort of markings more clearly. I mean, it's possible because this is burnt out. Sometimes this paint changes colour. Let's get it unsoldered now. Well, as best I can say, this is yellow, green, black, brown. So 4, 5 ohms, 1%. Another good reason that would be the case is if you notice the yellow band is like on the fatter part of the resistor, it's nearer to the lead than the brown one, supposedly. And the end which is nearest the end of the resistor, the end of the coding nearest the end of the resistor, is the first digit. So yeah, I mean, that's the best I can say with that. If that really is a 45 ohm resistor, then let's work out what the current would be flowing through the LED and the opto isolator, assuming, because it's only an assumption, we have a 12 volt supply. Let's see. So current I equals V over R. Now we don't have to worry really about the voltage drop of the LED because the current flowing through the resistor and the current flowing through the LED is the same. So if we can see the current flowing through the resistor, that's good enough for me, yeah. So the resistor is probably a 45 ohms. I equals V over R. V, we're going to guess, 12. Certainly less than 16. Divided by 45. 266 milliamps. That's never right. So it ain't a 45 ohm resistor. That is for sure. Even if the voltage was much less, like say 5 volts divided by 45 ohm resistor, there's still 111 milliamps. So it ain't a 45 ohm resistor. So what is it? Well, sure as hell it ain't going to be a 1 meg, because we're going to have then, say, 12 volts divided by 1 million. This is 120 microamps. That I'm sure is just way too low. A milliamp or two might do it, but that is low. So what is this resistor? Well, first thing, it is a resistor, R2, R1, so it ain't something else. It's got to be a resistor because we can see what it does in the circuit. We'll just try to measure it again out of circuit. Definitely open. Okay. I suppose the other way to go at this is to work out what current we may expect to have in an opto-isolator LED, and then work out what resistor value we would need if we again estimate the supply voltage. There's another thing with this as well. This opto-isolator is not just a run-of-the-mill opto-isolator, as I mentioned. We can see the maximum forward current for the LED is 60 milliamps. So this can't be anything as low as like a 45 ohm resistor. We can see this graph. So this normalized CTR. CTR is current transfer ratio. And it's showing here that the LED current can be down below 100 microamps in actual fact, and we'll be on this part of the slope. So it's possible it does operate with as high as a 1 meg resistor. Again, there's a couple of things that don't make a lot of sense to me. The fact this resistor was burnt up is another thing that makes me wonder, would this be a 1 meg resistor? Because the current flowing through it will be so low. I don't see how you could burn it out unless there was something wrong in this part of the circuit and too much voltage was getting to here. Maybe if that was the case though, the capacitor would explode. Come on. Yeah, if there's enough voltage across that resistor to burn it out, there's more than enough to blow up that capacitor. So what I'm going to do is I'll take the capacitor out, I'll put a new one in, and then I'm going to measure the voltage across the cap. So the resistor's not fitted at the moment. We know the opto-isolator is also blown on the LED. We can double check that, but I'm sure that's what I found before. Okay, so diode mode, open. It's not blown. Okay, so in actual fact, when I tried to measure this in the circuit, I couldn't measure that. That actually reads okay. I bet we can even test this actually with 2 multimeters. I mean, it's basically 1 volt, that's what you'd expect. Let's test the opto-isolator, and then as I say, let's just power this up and see what voltage we have across the capacitor once I've changed the capacitor. Okay, this one's on diode mode, this one's on ohms range. What do we have? Let's see if we can light the LED. We can, and it works. You can see it's turning the transistor on there. So we can say the transistor does switch on. I think that opto-isolator is absolutely fine now. I'll change this capacitor and let's look at the voltages. Okay, I've replaced the capacitor for 70 microfarad, 16 volt. I've decided to replace the resistor with a 1 meg, and I've put a 1 watt resistor in. So because I don't know why this failed, I've put the 1 watt in. Can't do any harm. It's quite possible now I think about it. The reason this is a Darlington transistor, which has an extremely high gain, the datasheet says at least a gain of 500. That probably means that very small fluctuations in the brightness of the LED will cause large fluctuations on the output, yeah. And this may well be operating right down at the limit of the LED. That's how it can detect brownout. So it kind of makes some sense when I think about it in that way. I'm going to power this up just as it is, and let's see what voltage we have on the capacitor, and let's see what happens on the output of the opto-isolator. And just before we do that, let's clean all this crap off it. I've mounted the PCB on upside down for a moment, just stops it flapping around because there's mains voltage on this. I'm going to check that capacitor as well. I can't remember if I did this previously. So the capacitor is here. Yeah, these are a bit bent. So that reads 470 nanofarads, near enough, 460 something. Happy with that. I doubt then there's any leakage resistance here. Wouldn't really make sense because the capacitor reads okay. And you probably wouldn't be able to tell without a mega high voltage resistance meter anyway. Nah, looks okay. So power on. We're on. What do we have on the capacitor? Uh, 28 volts on a, okay, fine. The other one was a 16. 28 volts on that, that's interesting. I would have put a higher voltage capacitor in than that. I don't like that at all. How about across the opto isolator? Yeah, so switch it back on again. 0.852 on the LED. And yeah, 27 on the capacitor. That doesn't look like it's enough to run the LED in the opto isolator. I can test this by seeing what happens on the transistor side. And B, that capacitor ain't going to like that very much, yeah. Let's go to ohms range. So across here, should probably just read open at the moment. Yeah, switch it on. Still reads open. It's possible then I have the value of the resistor wrong. And because there's no current being drawn from the output of the bridge rectifier, therefore allowing the capacitor to discharge a little bit, I see a higher voltage than I would expect. So we're down to the mystery, guys. This requires a 4 AM moment to see if I can come up with anything else. But the question is, at the moment, what value is that resistor supposed to be? And do you guys think I approached this in the wrong manner? Hey! And actually, I know what one of you is going to say, so let me just try something first, just to eliminate this suggestion, because it's going to come otherwise. So again, get a contact on here, and then try to get into this. And that reads 300 odd ohms. Maybe about 8 or 900. That's probably the last place I can get a connection. That would suggest then that this is something more than 500 ohms. Maybe towards a kilo ohm, but the markings make absolute no sense. Normally I wouldn't bother too much with the current limiting resistor on an opto isolator. But I've got a feeling this one is doing something a bit more critical, as I've maybe alluded on, some sort of brownout detection. And if that's the case, well, I guess if I put too low a value in, the brownout just won't work anymore. But, you know, if I have to do that, I will do that. But I'm interested right now to hear what all you guys watching, especially you in the corner up there and down there, think about this, yeah? What do you think the value of this resistor is supposed to be? And what do you think this circuit is actually doing? Do you agree with me? Do you disagree? Well, we can get down there and talk about it, yeah? Looking forward to hearing from you and looking forward to seeing you all soon again on Learning Electronics Repair. Ciao for now.